this would be the video for the two questions, one of which is the last question we haven't answered during the revision, and the other one is the one given by Jeremy. Okay, so let's begin. So for this particular question here, you are actually given this particular equation. K is equal to A times the constant E raised to the power of negative C over T. Now, before you answer this, you have to read the given because this is very important. So here, the variables that we are trying to relate are K and T, the temperature T, whereas A and C are considered as constants. So you can think of them simply as numbers. And of course, E is also a constant. Okay? Also, our temperature would be greater than zero. It means the temperature is positive. So for the first task here, you are actually asked to show that the derivative of k with respect to the derivative of k with respect to t is always positive. So here we have to solve for the derivative. So we say dk all over dt is equal to. So since a is a constant, all right, so using the laws or the rules we have in derivative, so we can just write this as a, and then derivative of e would be the same as e still, power of negative c over t, and multiplied with the exponent, the derivative of the exponent, negative c over t derivative. All right. So if we continue, this is now equal to, we have a, so we have times e to the power of negative c over t. And this, for this one, you have to remember that c is a constant. So it's just simply a number, and it is the t that is considered a variable. So to make it easier to find the derivative, we can rewrite this as negative c times t raised to the power of negative 1, and we find the derivative of this. Alright, so this is now a times e to the power of negative c over t. Applying the appropriate law for differentiation, this now becomes, let's use another color, negative 1 multiplied with negative c times t, this time power of negative 2. Okay, so if we try to simplify this, this is now equal to a times e to the power of negative c over t, all right, multiplied with two negatives becomes positive c over t squared. Or if you want, you can retain it as t power of negative 2. It's still the same thing. Now, since this is not what we wanted to show, since what we wanted to show is to show that the derivative is always positive, it would be a lot easier to analyze if we keep all things positive. So if we are to find a way on how to remove the negatives, because in that way, analysis would be a lot easier. So that's why I told you later a while ago that you can still write it as power of negative 2, or you can just simply simplify it as over t squared. Okay, so for this one, to eliminate the negative exponent, we have to put it down. Or we have to find the reciprocal of the entire expression. Okay, and by doing so, the exponent now becomes positive. So this is now equal to, if we continue, a, find the reciprocal of the second factor. This is now 1 over e. This time, the exponent now becomes positive c over t. All right, times c over t squared. Okay, or if you wanted to really see it consistently, I can erase this. For example, let's replace this with positive c t power of negative 2. Okay, so that you can connect it with the continuation, the one that we just have written. Okay, so if we combine all these in one expression, we can now write this as a times c all over, you have e to the power of c over t times t squared. Okay? Again, let's go back to the given, to all the given. A and C are positive. So for this one, since A and C are all positive, so the product of two positive numbers would also be positive. Okay? So we have, let me erase this. So we have a positive numerator divided by, and then in the denominator here, C is positive, T is also positive. All right? That means E raised to a positive number would be positive. Likewise, we know already that the temperature is greater than 0. That means when you square a positive number, you will also get a positive result. So the product of two positive numbers would also be positive. In other words, you are actually dividing two positive numbers. That is why we could already say that the quotient when you divide two positive numbers will also be positive. And hence, we already have shown that the derivative would always be positive. Okay? So that's the reason why I said it would be a lot better if we can make the exponents positive, or if we can um, do away with the negative exponent, so that when we analyze it will be a lot easier. So that's for letter A. This time, let's now go to the second one, the next one. So for this one, you're actually asked to sketch the graph of k against t. All right? So remember that in the equation, let's try to go back to the equation here. In the equation, k actually takes the place of your dependent variable. So this one acts like your y, and your t here is the independent variable. It acts as your x. Okay? So this actually is very helpful when we do the sketch. Take note that here you are not asked to make a accurate an accurate sketch. You just are to make a rough sketch. So when we make our Cartesian plane, sorry. So if we are to make our Cartesian plane, all right. So we have to label this one properly. I'm sorry for the plane itself. This is just a rough sketch. Labels properly. Remember, t acts as the independent, so it's the x, and then k acts as the dependent, which is the y. So k is here. This is very important when you make the rough sketch. All right. So here you can see that the limit of k when t approaches 0 is also 0. So this one is very, very clear. The limit of k when t approaches 0 is 0. So when your t approaches 0, the limit of k is actually 0. All right? So that's pretty clear. Again, take 2. When your t approaches 0, so we go to the right, to left rather, sorry, because we approach 0. Now, there's no way for us to use this one because t is always positive. Okay? So, when your value of t goes closer to 0, the limit of k is 0. So we start at this point. However, when your t approaches positive infinity, if it goes here, okay, your k somehow approaches a certain value which is equal to a, but never goes beyond it. So it goes closer and closer, but never goes beyond it. So we can expect this to be your asymptote, or this could just be your boundary, your limit. So for us to do that, we have to identify some sort of an a value from the graph. So let us say, this is just an estimate, let us say let's try to have this point here as our A. Okay, take note, this is just a rough estimate. This tells us that as our t approaches positive infinity, this one, k tends to approach this value of a. It approaches this value of a but never touches it. That will be our boundary or our limit. All right? So we start from 0 and then we somehow go up to the right but never goes beyond the a. So how or what shape of the graph would it, what would be the shape of the graph? So going back to your equation, we have here an exponential equation, some sort of an exponential equation. Okay? So if you try to look at your calculator, the graph actually looks like this. Sorry, it looks like this. It's a curve. So we can somehow estimate that the graph would somehow be starting from 0, and then as we approach positive infinity, it actually goes up, and it looks like this one. But it will approach A but never touches A. So this is now the rough sketch of this given conditions. All right. Next, let's now go to the next one, letter C. Okay. For letter C, you don't have to be afraid with this Arrhenius equation. This is just a name, but this doesn't have a bearing on how to solve it. Still, whatever topic we've discussed is the one applicable to solve this one. Okay? So the Arrhenius equation predicts that the graph of ln k against 1 over t is a straight line. Write down the gradient and the y-intercept. Now, let's go back to the given. If you recall, let me just have the given. Yeah, the given is, let me write it in black. We have k is equal to a times e raised to the power of negative c over t. Let me enclose it with a red box. All right. Now, according to this Arrhenius equation, it somehow predicts the graph of ln of k and 1 over t. It's ln of k and 1 over t. However, the equation we have is k, not ln of k. So we still have to modify this in order to get an ln of k. So how to modify this? You just have to introduce the ln, both sides. However, since this one is not suitable to be, it would be difficult if we have it at this form, no? If we introduce ln in this particular form, it will be difficult. So let's try to rewrite it in a way where we can apply the laws of logarithm. I hope you still know your laws of logarithm. So let's rewrite this in a way we can apply the laws of logarithm. So we have the quotient law. So we can write this as k equal to a. Since we have a negative exponent, we can just find its reciprocal. The exponent now becomes positive c over t. All right. So from here, we can now introduce our ln, both sides. Okay. Thus, we now have, let me write it to the left, ln of k is equal to, applying the quotient law, this now becomes ln of a minus ln of e raised to the power of c over t. All right. So from here, we can now simplify it as ln of k is equal to ln of a, and the ln of e, you know that already, will just be minus c over t. When you take the ln of a natural number e, the result will be its exponent. Okay? Now again, let's go back to the original given. Here, it says that the graph of ln of k against 1 over t. That means, if we analyze it, this acts as our y, the graph of y against the graph of x, and this is our x. Okay, so 1 over t is actually our x. All right, so to further analyze it, we can write this as ln k equals ln a minus 1 over t times c. Let me write this in um, red instead so that I can emphasize the variables. So ln k, and then this one is 1 over t. Remember that this somehow serves as our y, and this somehow serves as our x. Sorry, let me use other colors. This somehow serves as our y, and this somehow serves as our x. Why sir? Why did you say so? It's actually found in the first portion. Predict the graph of ln of k against 1 over t, which is a straight line. So from here, we could deduce that ln of k serves as our y and 1 over t serves as our x. Okay? So in a straight line, we know that the equation is y equal to mx plus c, wherein the numerical part or the numerical coefficient of x is your slope. This is your gradient. And the constant part is actually your y-intercept. Okay? Now, for us to easily compare it with y equal to mx plus c, I think we need to rearrange the terms in this one, the ln k. So if we rearrange the terms here, we can now write this as ln k equal to, we write negative 1 over t first, then c, or instead, let me erase this one. To make it consistent, no, let me use red color. Ln of k, then you have negative c 1 over t, then you have plus ln of a. Okay, so again, remember that this serves as our y and this serves as our x. And from here, it's now pretty clear that the numerical coefficient of our x, which happens to be 1 over t, is negative c. Thus, we say for the first one, the gradient, the answer to this is negative c. This would be our gradient. That's the numerical coefficient. It's negative. And for number 2, all right, the y-intercept is the constant part, which is actually equal to ln of a. This is now our y-intercept. Okay, and that's how we can actually solve letter C. All right, this time let's proceed to letter D. So for the next one, you are given a table. It says the following data are found for a particular reaction where T is measured in Kelvin and K is measured in this particular unit. So I'm not really familiar with this one. Okay, so we are going to find the equation of the regression line for ln k on 1 over t. Okay, so we need to find the equation of the regression line. However, you have to take note that the table shows us t and shows us k. But what we wanted to find is the regression line for ln of k and 1 over t. Hence, we need to come up with another table. We can use the data on the table, but we need to revise it. So we need to come up with another table. Okay, wherein we have 1 over t and we have ln of k. All right. So let's now put in the data here. The data would be 1 over t, so that's 1 over 590, and it is being paired with ln of 5 times 10 raised to the negative 4. Okay? And then we have 1 over 600. And this one is being paired with ln of 6 times 10 to the power of negative 4. We also have 1 over 610 paired with ln of 10 times 10 to the negative 4. One over 620 ln 14 times 10 to the negative 4. Also, we have 1 over 630 paired with ln of 20 times 10 to the negative 4. And 2 more to go. We have 1 over 640 ln of 29 times 10 to the negative 4. And finally, we have 1 over 650 paired with ln of 36 times 10 to the negative 4. Alright. So this would now be the data that we're going to use. Alright, so you can take a screenshot of this because we need to go to, or no, it's okay. Let's try to see if I can. Yeah, I think I can. Oh no, I think we need to take a screenshot of this so we can go to our calculator, or if you want, you can use your calculator directly, and let's put in these values. So what I do is just to put in directly. Okay, I mean, like the way I've written it, that's the way I will put it here, so I won't be confused. So the first one is 1 over 590. So I'll go to math. This one, that's 1 over 590. 1 over 590, not 59. Wait. Okay, this one. Next, I have 1 over 600. I don't know if there's an easier way to copy this, but if you know a trick on how to copy this one, it would be a lot easier. Then you just have to change the values. Then math, 1 over 610. Okay, math, 1 over 620. Or if you want, you could also do it something like this. Wait, let me just finish this. 1 over 630. If you don't want to have it 1 over 630, 1 over 610, you can write it as 640 and then exponent of negative 1. That's also fine. That's the same thing. Okay, let's try to see 650 exponent of negative 1, just to make it faster. So it depends on you actually. And then the other one, we have ln. Ln of 5, and then you can see here the 10 to the power of x. That's 10 times a certain value, so negative 4. Okay. Wait, go to 10 times. Let me just delete. Go to, wait, clear. Let me clear this one. Okay, ln, let's try. We have 5 times. Let's try to put times here. 10 to the power of negative. Okay, I know now. Negative. You have to use the symbol negative 4. So I can just delete this. Delete. But make sure to use the symbol negative 4, not the minus symbol, because that will be an error. Yeah, that's it. So again, ln of 6, and then you have times 10 the power of negative. Use the symbol negative 4. ln, you have here 10 times 10 to the power of negative 4. Oh, sorry. Ln of 10 times 10 to the negative 4. Then ln of 14. 14 times 10 to the negative 4. Then ln 20, no? 20 times 10 to the negative 4. And then 29, ln of 29 times 10 to the negative 4. Okay. And then lastly, 36. 36 times 10 to the negative 4. All right. I think that's it. So since we now have this already, we can just go directly to stat, calculate linear regression. So we have, it's already preset, L1, L2, no need for frequency list, no need for store, calculate directly. And we now have these values. Okay? So this now gives us the equation of the regression line. All right? So the equation now, let me just copy it first here, and then I will show it to you in Jamboard. So the equation now is y equal to, so our slope here is negative 13,383.19 plus the y-intercept is, let's copy all the values for the y-intercept, because for the y-intercept, if you recall, it's ln of a. So we need all the values when we solve for ln of a later on. 15. You will see it later on. The moment we solve for the task in the problem. 0.0107228. Okay. Let's now go back to Jamboard. So this is now the equation of the regression line. This time, we now solve for C. So if we recall here, our C, our gradient was actually equal to negative C. Take note, the gradient is equal to negative C. So whatever value of the gradient that we have, that's equal to negative C. I repeat, it's not just C, it's negative C. So if we go back to this, the gradient that we got is negative 13. So this particular gradient is equal to negative C. Sorry, this one, so that you won't be confused. So this one, let me just put it inside the box. Because if I'll do it like that, you might think it's a division. This one is actually equal to negative C, whereas this one is equal to ln of A. Okay? So if you try to look at it, negative C is equal to this, therefore C will just be equal to the positive of this. So we can eliminate the negative symbol. So C now is equal to 13,383.19. Okay. Whereas this 15 is equal to ln of A. That means we still need to solve it. So we say ln of A is equal to 15.0107228. Remember, how do we solve ln? We have to introduce an e, and this becomes the exponent. This one will also be the same thing. Whatever we do to the left, we also do to the right. Therefore, from here, we now say a is equal to, use your calculator. That's why I said you copy the entire value for the y-intercept, because we still need to do something about it later on. So click this one. So we have e to the power of, we have 15.0107228. And this gives us 3, 3, 3, 3, 258.99. So this is now the value of RA. You might see that in the marking scheme, this one is rounded off. But there's also a portion in the marking scheme which gives the entire value of this, which is also correct. So you might be asking me, sir, how many values should we round it off to? There's no certain number of values except if the question tells you how many times that particular answer should be rounded off. If there's none, then you can just round it off according to your choice. But usually I always tell my students to round it off to 2 decimal places if possible. Again, you have to read instruction for you to know how to round it off. And this is the first question.